Hello, everyone. It's time for another inner chapter. So today we're going to be working on inner chapter C, and the real focus here is going to be going back over chapter 7, but really looking at the influence of how orbitals modify our reactions. So, time to look in frontier molecular orbital theory. So it's a whole bunch of homo lumo. So, previously we've went ahead and examined our 10 major elementary steps using Lewis acid notation. So we always go ahead and start with our electron-rich species and going to our electron-poor species. However, it's really important to note that these electrons aren't just simply sitting here as these lone pairs or bonds. These electrons really exist in movement around in these orbitals. So if we want to be able to track what's happening with the reaction, we have to look at how these orbitals are changing. And it is worth noting that this will give us a lot of information about what reactions are allowed or forbidden, which reactions might be a little more favorable than we'd expect, which reactions might be a little less favorable than we expect. But most importantly, as we're moving forward, when we're talking about the physical arrangements, this is really going to dominate a lot of those constraints. And again, since these reactions are dominated by how we're moving from electron-rich to electron-poor atoms, what we can do is really examine how these correspond to certain orbitals. So what orbital are my electrons located in, and what orbital are they moving into? So when we do this, we quickly find out that we find our HOMO and LUMO. So if you remember, our HOMO corresponds to the highest occupied molecular orbital. So this is going to be the orbital with the highest energy of all of our orbitals that contain electrons. So as a result, this is going to tend to be located on our electron-rich species. Our electron-rich species has more electrons and they're more likely to move. Now, where can these electrons move? So our electrons are going to have to move into an empty orbital. So the easiest orbital for them to move into is going to be the LUMO, that lowest unoccupied molecular orbital, or pretty much the lowest energy orbital that has a hole. So we're going to be looking how these electrons move from the HOMO of our electron-rich species to the LUMO of our electron-poor species. Now, when we focus on these two orbitals, this should be the HOMO on the electron-rich species should be the highest occupied molecular orbital for the whole system. And similarly, when we look at the LUMO for our electron poor species. So as a result, these are going to be the overall highest and lowest orbitals. So these orbitals are on the frontier. Not surprisingly enough, any model that focuses on these HOMO-LUMO pair is known as frontier molecular orbital theory. So when we're looking at these frontier molecular orbitals, what we're going to find is that when I mix these two species, I would expect the electrons to move from one to the other. Now, when they do that, this is going to generate an overlap in between these orbitals as they're actively moving from one to another. Well, this movement of electrons through this intermediate space is going to be our transition state, which means that if I can go ahead and model how these two orbitals mix, I have a prediction of what my transition state looks like. So the real focus of frontier molecular orbital theory is saying that transition state energies and the transition state itself can be modeled as an overlap in between these two frontier molecular orbitals. The better that overlap, the lower in energy our transition state. So a really good transition state is going to have very good overlap in between that HOMO-LUMO. A very bad transition state would have a very poor overlap. And so as a result, the more I'm able to stabilize that overlap, the lower in energy my transition state, the more easily I should be able to move in between reactants and products. So again, the real focus of frontier molecular orbital theory isn't going to be saying whether or not I can move from reactants, whether the products are favorable or unfavorable. It's whether I can literally move from one to the other. If I can't, then that barrier is too large to see any interconversion. So if that HOMO and LUMO orbitals have a very substantial overlap. That means that transition state is favorable, should be lower in energy, and that transition state is said to be allowed. Now, if those orbitals have very little overlap, I can't make the electron smoothly move from one to the other, then that reaction is said to be forbidden, as it's just too hard to move the electrons from one orbital to the next. However, what we can also use is something called the principle of microscopic reversibility. So this states that if I know that an elementary step allows me to move from reactants to products, it should correspondingly be easy to move from products to reactants. So if the forward reaction is allowed, the reverse reaction is allowed. So as a result, we only really need to prove that we can that the orbitals will allow us to move in one direction to show that we can actually do the reverse reaction. And that's really important because, as you may remember, many of our reactions tend to come in pairs. All right, so now we're going to go ahead and look through all of our major elementary steps. And using this, we're going to be able to explain several phenomena that we'll explore later. Mostly any geometric constraints of how I can bring my two molecules together and what result this has on product stereochemistry. So let's go ahead and start with our classic elementary step, the proton transfer. Literally, moving a proton from one molecule, our acid, to a second molecule, our base. Now, as we saw in the last chapter, we can also frame this in terms of electron-rich and electron-poor. So in this case, our electron-rich site is always going to provide that HOMO, and our electron-poor site is going to provide the LUMO. So in this case, it's going to be my base that is going to be electron-rich. It has the electrons. And these electrons are typically going to be in the form of a lone pair. And lone pair electrons are always on non-bonding orbitals. So traditionally, this is often going to be in an sp3 hybridized orbital, but you can also imagine in special cases them being on an sp2 or sp hybridized orbital. The most important thing here is it's on a non-bonding lone pair electron. Now, let's go ahead and look at my electron-poor species. So again, in the electron-poor species, it turns out that my LUMO is actually going to be that anti-bonding orbital. So electrons can move from that non-bonding orbital into that anti-bonding orbital. As I fill that anti-bonding orbital, I should then break the bond, because if I have equal filled bonding and anti-bonding, well, then the whole bond falls apart. Now let's go ahead and look at what this looks like from more of an orbital picture version. So in this case, my HOMO is again on that sp3 hydroxide group, and it's going to overlap with that LUMO. Again, this HCl antibonding orbital, where I have the S orbital on the H and that P or hybridized sp3 orbital on that chlorine. Now, in order to go ahead and transfer electrons from that oxygen to that hydrogen, I need to overlap these orbitals. Now, this means that that base needs to approach head on to that HCl bond. Because again, I'm not just injecting those electrons in the s orbital, I have to inject it straight into that antibonding orbital to make that s orbital break free, and again, break that bonding and antibonding. So this dictates that I would expect most proton transfer to happen along a straight line from the molecule being made to the molecule accepting the hydrogen. Now, if I try to approach that that hydrogen from any other angle, we're going to find that we have essentially a forbidden contact. If I try and come in from above or from the side, I don't just overlap with that hydrogen, I also end up overlapping with that chloride bond as well. And this will essentially generate a repulsion field, again, forbidding this overlap. So the only way we can go ahead and perform a proton transfer is through, again, this head-on direction, as the hydrogen pops from one bond to the next. Now, we can apply the same basic principles to other elementary steps, and we can go ahead, as usual, start with the step that is the most similar mechanism to a proton transfer. That's an SN2 reaction. So in this case, I again have electron rich species. Now we term it as a nucleophile. And our electron poor species, also now known as our substrate. We can start by examining the same process in curve notation. So I'm going to start those electrons moving from my nucleophile, and they're going to attack that carbon atom of the electrophile, because again, that carbon should be the electron poor species. Now, since our nucleophile is going to be our electron-rich species, this should provide that HOMO orbital. Again, it's going to be another non-bonding orbital, such as in this case, an sp3 hybridized orbital. Now, if I take a look at my electrophile now, well, in this case, we're still going to be adding those electrons straight into an anti-bonding LUMO, because again, I'm going to be breaking that bond. Now, the big difference is previously when we had a hydrogen atom, that was an s orbital. Now that carbon is going to provide essentially that p orbital. So again, this LUMO is produced by the overlap of two hybrid orbitals instead of one hybrid, one s orbital. And that really helps illustrate that, again, in order to overlap with that anti-bonding orbital, I again have to approach from that opposite side of my leaving group. So as the anti-bonding orbital should have essentially a lobe of electron density on the opposite side of the bond. And this is going to be very heavily expressed. So this is going to be the orbital that I'm going to be injecting those electrons into, then breaking the bond and pushing the chloride off from the opposite side. So again, we have to have that straight on attack. In contrast, we can find that we wouldn't expect any electrons to be able to attack from essentially the side, as again, we'd overlap with both, we'd have both constructive and deconstructive interference from this direction. So again, it has to be that head-on attack from the opposite side of the leaving group. Now, because we have to attack from that opposite side, SN2 reactions are also said to undergo backside attack. If the front side is that leaving group, the backside is this open area of electron density. And the HOMO comes in, places the electrons right there, pushes the chloride out. Now, we can also extend this to other elementary steps. So the next major one we dealt with was the coordination step. So again, in this case, my nucleophile is a Lewis base, and my electrophile is a Lewis acid. So again, just as always, that electron-rich species is providing the HOMO. Again, and this time, it's that non-bonding orbital, so nothing's changed too much. Biggest difference, again, is on the electrophile. This time, instead of the LUMO being an anti-bonding orbital, it's actually going to be a non-bonding p orbital. Because remember, when I have a carbocation or any sort of octet vacancy, that means I always have an uncoordinated p orbital. Thus, all of my species with an octet vacancy should be in a nice trigonal planar geometry, sp2 hybridization, very nice and flat. Now, it's this unhybridized p orbital that's going to make that LUMO that I can bring that bromine in to go ahead and interact with. So again, in this case, our electrophilic center is always going to be trigonal planar in a coordination view, which means that it's possible for my nucleophile to approach from one of two directions. I can actually get very good overlap with that p orbital if I either come from the top or from the bottom. So either side, I can make that direct overlap with that empty p orbital. But again, as a result, I'm going to want to make sure that my incoming hybrid orbital essentially comes in perpendicular to the plane of the molecule. This is going to maximize that overlap. And again, giving me the best overlap, meaning giving me the lowest energy transition state. So again, that high degree of HOMO-LUMO overlap is really what's going to allow for that formation of the sigma bond. Eventually, I will mix these two mix these two orbitals, that p orbital will hybridize, and I'll make a nice, good sigma bond, generating that tetrahedral geometry. Now, that gave us the forward direction. But remember, we also have that reverse reaction of a coordination. So the forward reaction is coordination. The reverse reaction is heterolysis, where I'm going to take this nice bond that I just made, and I'm going to pull the electrons back off to go ahead and release that nucleophile. So again, in this case, I would expect that HOMO to now be that sigma bond. So this sigma bond is going to overlap, split. The electrons are going to move back onto that iodine, more or less, again, splitting it into its two component non-bonding atomic orbitals. Again, forward direction, I started with two atomic non-bonding orbitals, made one bonding orbital. Heterolysis is literally just taking that bonding orbital and splitting it back into its two atomic orbitals. Now, again, in this case, the electron should always follow that more electronegative atom. So that more electronegative atom reforms our HOMO group on that electron-rich nucleophile. Now, we can go ahead and continue this process now, instead of looking at substitution, to addition reactions. So in this case, I'm going to take that same nucleophile, still going to end up providing that HOMO in terms of that non-bonding orbital. But again, we've now changed our the lowest unoccupied molecular orbital on our electrophile once again. This time, that LUMO is going to be that pi anti-bonding orbital that's located on that polar double bond. Now, that means that when I'm looking at the interactions in between this nucleophile and electrophile, I have to look at this overlap in between this non-bonding orbital and this anti-bonding orbital. And again, really important to note that a pi orbital tends to be more located on the more electronegative atom, as again, it steals the electrons in the bond. Contrastly, that means that any pi star or pi anti-bonding orbital is going to be more centered on that less electronegative atom, meaning that that pi star orbital is mostly going to be focused on that carbon atom. So this is going to direct that nucleophile to go straight to that carbon center. And if we take a look at the orbital picture, this is exactly what we see. There is some of that pi antibonding character on that more electronegative oxygen, but most of the character tends to be located on that carbon. So this means that I'm going to again try and generate a direct overlap, bring that nucleophile's non-bonding sp3 orbital, point it straight at that p orbital that's contributing to that anti-bonding orbital. This is going to generate that maximum overlap. And again, this time, instead of that direct head-on overlap from the nucleophile is going to be that perpendicular to the plane of the molecule. So it is straight on with that p orbital. So as this orbital approaches that pi star orbital, that's going to start to break that pi bond. Because again, if I start occupying an anti-bonding orbital, this means that the bonding and anti-bonding, in this case, that bonding and anti-bonding pi, ends up breaking apart into its two atomic orbital components. So that's going to force the electrons in this orbital back onto a non-bonding orbital on that more electronegative atom, in this case, on that oxygen. Now, again, if the forward direction is allowed, so is the reverse reaction. So again, following that principle of microscopic reversibility, if I can go ahead and bring that chloride to break that double bond, it also means that I can push that chloride off by making a double bond. In this case, I switch who my HOMO and LUMO is. Now that highest occupied molecular orbital is going to be on the non-bonding orbital on the electronegative atom, and my LUMO is going to be that sigma anti-bonding orbital to essentially my leaving group. So as that electron moves back over, the electrons are going to move from that occupied, interact with that with the p component of that antibonding orbital pushing off my leaving group. So walking that whole process in reverse. And again, as these electrons move back, I'm going to reform that pi bonding orbital and then that non-bonding orbital again on my original nucleophile. Now, this gets us to one of the trickiest cases, the bimolecular elimination step. So the big problem with bimolecular eliminations is in this case, I am forming two bonds. Again, my base to my hydrogen atom that I'm extracting, as well as forming a double bond. So I've got formation of two unique bonds, which means that I really kind of need to look at these two parts. I'm going to look at how the orbitals form that first bond and then how the orbitals form that second bond. So in that first step, it's going to be my base that provides that HOMO. Because again, my base is the electron-rich species. And it turns out that it's going to be a CH bond that's going to form that electron poor species. So it's going, so in this case, my LUMO is now going to be that sigma antibonding orbital. So as I form an overlap in between this non-bonding and this antibonding orbital, I should be able to break that CH bond. And then in the second step, I can use that breaking sigma bond orbital to essentially mix with another sigma antibonding orbital to reform a pi. And again, a leaving group, which has to take its non-bonding orbitals and go home. So let's take a look at that first step. So the first step looks like a simple proton transfer. My hydroxide is coming in with its non-bonding orbital, overlaps with that antibonding orbital. That hydrogen and s orbital is gaining electrons, so we've got a good interaction here. I'm pumping electrons into that antibonding orbital, which essentially is going to allow the breakage of that sigma bond, the breakage of the CH sigma bond orbital while I'm forming an OH sigma bonding orbital. Now, it turns out that, again, as that sigma antibond, as I'm occupying that sigma antibonding orbital, I'm breaking that sigma CH bond. This can now act as the HOMO for the next step. Because as I'm increasing the energy of both this antibonding and bonding orbital, it now is higher in energy, making it the HOMO in the highest occupied molecular orbital in the remaining molecule. So now it can donate its electrons into the LUMO. So the LUMO is actually going to be the sigma antibonding orbital to that leaving group. So as the electrons are going to move from the HOMO into the LUMO, you may notice if these two orbitals are set up in parallel, there is a huge overlap here, and it already kind of looks like a pi bond. So as I break bonds to these to that hydrogen bond atom and that leaving group, I'm going to form a beautiful pi bond. But in order to do this, it turns out these two orbitals need to lay adjacent to each other. One of the best ways we can do that is by ensuring that that carbon leaving group bond and that carbon hydrogen bond are in that anti-configuration. So again, that E configuration we saw in alkene chemistry. If these two groups are anti to each other, it means all the orbitals line up beautifully. Thus, again, we're looking at whatever beta hydrogen position is being deprotonated in a bimolecular elimination should always be removed from that anti-configure conformation. And if I try and remove that proton from any other position, such as the one on the same side, also known as the syn conformation, well, at this point, you're going to notice that our orbital overlap is much lower. As this orbital overlap decreases, we start to enter that forbidden region, meaning that I can't go ahead and just make a beautiful pi bond from this. So again, this is going to be far less favored than a similar system in the syn conformation. So as a result, one of the things we're going to explore in chapter 8 is that that H atom, because it's always removed from that anti-position, is really going to dictate what stereochemical products can be produced from this reaction. All right, so that leaves us only two major classes, the next of which is going to be electrophilic addition and elimination. So again, one of the big things that changes when we move to electrophilic addition and addition reactions is we finally deal with a system where my nucleophile isn't in a non-bonding orbital. In this case, my nucleophile is actually going to be an electron-rich pi bond. So it's going to be this pi bonding molecular orbital that really is going to be my highest occupied molecular orbital, or that HOMO. That means that my lowest unoccupied molecular orbital is going to be on that electrophile, and it's going to be the one that provides the LUMO. Now, one of the things to note is we had many different electrophiles we can use in practice. And the exact LUMO that is provided, whether it's a sigma antibonding or a non-bonding, is going to be entirely dependent on what electrophile is being used. In this case, we're going to be looking at a proton electrophile. So again, this is going to be a nice sigma antibonding orbital, same thing we more or less saw in proton transfer. So we can go ahead and look at a very proton transfer-like mechanism. The biggest difference here is that now that's that sigma antibonding orbital has to essentially approach from either directly above or below the plane of my nucleophilic pi bond, because we need to essentially come straight from above or straight from below to make sure I get good overlap in between that hydrogen atom and that pi bond. When I do this, this will essentially inject the electrons from that HOMO into the LUMO as part of the transition state. So as I have this essentially perpendicular approach, is going to maximize that overlap from my electrophile to that pi bond. And again, as that electrons leave that pi bond, we're going to end up injecting them into that orbital, making a nice sigma bond. But it is worth noting that this will leave an empty pi or p orbital on the remaining carbon atom. And again, if this is how things work for electrophilic addition, electrophilic elimination should also, again, according to the principle of reversibility, also be allowed, as it's that same reaction, but in reverse. This time, again, we have a little bit more straightforward reaction. In this case, we have the carbocation's non-bonding p orbital is going to form the LUMO, and the highest occupied molecular orbital, in this case, is often going to come from something like a base that will pull off a proton. So again, this is going to ensure that if, in this case, my leaving group, in this case, a hydrogen, as it exits, that sigma bonding orbital is going to need to be in a parallel position to that empty p orbital in order for electrons to move smoothly from that sigma bond, sigma orbital to that p orbital. And again, this should end up smoothly forming that pi bond. So this gives us all of our classic addition, elimination, and substitution reactions. This leaves us only one last major class of elementary steps, and that's the carbocation rearrangements. So in these cases, it's actually a little bit more simple, as I have a carbocation, which not surprisingly is going to be my lowest unoccupied molecular orbital. So it's going to be providing a non-bonding p orbital, same thing as I saw in nucleophilic addition and in my elimination reactions. But in this case, that highest occupied molecular orbital is actually going to come from a sigma bonding orbital, either from a sigma bonding to a C. In this case, for a hydride shift, it's going to come from a sigma bonding CH orbital. So in this case, you'll notice that if I have that sigma bond on an adjacent atom, these two, the sigma orbital and this empty p orbital are right next to each other. So what this lets happen is this electron-rich sigma orbital to kind of slide over. So that hydrogen is going to move smoothly from one to the other, as these two orbitals are close enough to have substantial overlap. And so this allows that H atom to move smoothly over to that neighboring empty p orbital. And again, you can apply the same principle to alkyl shifts. Biggest difference is then instead of being a sigma bonding orbital to a hydrogen atom, it'd be a sigma bonding orbital to an alkyl group, most likely, again, at methyl shift. But again, each time it's smoothly moving that sigma bond right to the next species. All right, so that's a quick overview of of all the elementary steps we covered from chapter 7, but this time from a molecular orbital perspective. So next time on the inner chapters, it's our last one, and we're going to go back to some fun nomenclature. Until then, take care.